Have you noticed how straight lines rarely survive in the cosmos? Light bends near mass, orbits curve, gas flows twist into spirals and filaments. Even the edge of a galaxy is a gradient, not a ruler's mark. The universe prefers paths that minimize action, not distance geodesics on curved space-time. Streams shaped by gravity and time follow a photon past a galaxy cluster and it arcs. Zoom out and matter forms a web, not a grid. Tonight, we'll ask why. What physics pushes nature away from Euclid's tidy plans? From turbulence to lensing to the cosmic web itself. If clear, steady explanations are your thing, a gentle like and subscribe helps others find them. Settle in. Let's see why straight lines break, bend, and blur when the universe gets a vote. People say the shortest path between 2 points is a straight line. But in the real world, that rule holds only in small patches. Over longer stretches, straight paths drift. Light does not keep a perfect track near heavy objects. Gravity pulls its path into a curve. Birds that migrate across oceans follow arcs because Earth is round. A river that begins as a narrow cut will swing left and right as it finds an easier drop toward the sea. Nature tends to favor shapes that spread force, share energy, and allow change over time. Loops, spirals, and bends do this work more gently than a hard, direct route. So it is fair to ask whether straight lines exist in nature, or if they live mainly in human thought. A line in geometry is an ideal object. It has no thickness and no end. It never wavers. The Greek tradition gave us clear rules for it, and those rules help us think and build. But the line on paper is only a model. It helps us plan roads and draw structures, yet it does not capture the full behavior of materials, light, and motion in a changing world. When we compare the model to the world, the gaps show up in useful ways. A common example is travel across the globe. On a flat map, a line from New York to Tokyo looks bent and long. On the sphere of Earth, the shortest route is a great circle, which is a circle whose center matches the center of the Earth. Pilots follow that arc because it cuts distance and fuel. It looks curved on the map because the map is flattening a round surface. The path is not trying to be clever. It is simply the nearest thing to a straight line you can have on a sphere. In math and physics, we call a path that is straight on a curved surface a geodesic. Locally, it feels straight. Over large scales, it traces the shape of the surface itself. Light also follows geodesics, and this is where space shows its hand. In everyday life, we learn that light moves in straight lines through air, and that is close enough for a classroom laser or a flashlight. Scale up, and details matter. Light changes direction when it passes from one material to another, air to water, air to glass, because its speed changes in the new material. That bending is called refraction. Light can also spread, cancel, or brighten when ripples overlap. That pattern is interference. Over long distances, small effects add up. Slight changes in air density can nudge a beam. Dust or temperature layers can scatter it. Nothing is perfectly rigid in practice. The biggest nudge comes from mass itself. General relativity, the modern theory of gravity, says that mass and energy bend space and time. Space is not a flat stage. It has shape that responds to what is in it. A star, a galaxy, or a cluster of galaxies will change the paths of light around it. The effect is called gravitational lensing. we can see a single distant galaxy appear stretched or repeated because a massive object lies between it and our telescope. The light is still taking the straightest possible path in curved space. The space is what is curved. Once you accept that, it becomes clear why straight lines at large scales are rare. The geometry itself is flexible. Materials behave the same way under force and change. A straight beam looks clean, but a slight bend often handles stress better. Curved bridges send loads into their supports with fewer sharp points of failure. A tree that bends in wind avoids breaking by spreading the push across many fibers. A river that meanders reduces its slope and sheds energy across bends rather than cutting a deep, fast trench. These patterns are not accidents. Over time, systems that can adapt tend to last. Curves help them adapt. Our bodies carry the same lesson. Blood vessels branch in a pattern that balances flow with the cost of building and maintaining tissue. Each split and arc reduces resistance and reaches more cells without wasting space or pressure. Airways in the lungs branch in a related way, trading a single wide tube for many smaller paths that add up to a large area for gas exchange. In both cases, sharp corners would cause turbulence and loss. Gentle curves keep the flow stable and reduce wear. Engineers copy this idea when they round pipe elbows or smooth the intake of a pump. We still prefer straight lines when we design. They are easy to measure, stack, and repeat. They give us grids for streets and frames for buildings. They help us organize ideas and data. But even the best tools for straightness have limits. A steel ruler changes length when its temperature changes. A wooden level can warp with humidity. A laser is close to perfect over a room, yet over many kilometers, tiny shifts in air can move it off course. When we zoom in or out far enough, the plane line becomes an approximation. That does not make it useless. It sets a range where it works well and points to where a curved description is better. Maps show both the power and the limits. We flatten the sphere onto a rectangle and keep certain features at the cost of others. A projection can preserve area or angle or distance along certain lines, but not all three everywhere at once. That trade is not a failure. It is a choice. In science and engineering, we make similar choices all the time. We use a flat Earth model for a football field, a spherical Earth model for a flight plan, and an ellipsoid for satellite work. Each is a level of detail matched to the task. Our brains notice curves in a different way than lines. Smooth shapes tend to feel calm and familiar because we see them in nature all around us. Hills, shells, waves, leaves. Sharp angles often signal man-made objects or hazards, so we react faster. Designers use this. When a device needs to feel safe to hold, its edges are rounded. When a sign needs to grab attention, it may use a bold, straight border. These are practical choices guided by perception and use, not by a claim that one shape is morally better. The point is simple. We live with both systems, but the raw world leans curved. At the level of motion, curves often come from balances of forces. Planets orbit stars because gravity pulls inward, while their sideways speed keeps them from falling straight in. The result is a path that closes on itself, a near ellipse for most planets. Galaxies rotate in huge disks shaped by gravity, angular momentum, and the history of how gas settled and cooled. The arms we see are not solid structures. They are regions where stars and gas crowd together as patterns move through the disk. These spirals form because density waves and differential rotation inner parts moving faster than outer parts set up a repeating pattern. Again, the system chooses a curved response. Even at small scales, where atoms and particles rule, straight paths are rare. On the scale of molecules, thermal motion makes paths jitter. In a fluid, tiny particles wander with random kicks. That is Brownian motion. In quantum physics, we talk about particles as waves that spread and interfere. We do not track a single, thin path the way we would draw a line with a pencil. We describe a cloud of possible positions and momenta and make careful measurements to narrow what we can say. The more precise the path you demand, the more you must disturb the system to learn it. The straight, unbothered track fades as a useful picture. If we return to space itself, the same theme holds. Space and time form a single fabric in modern physics. Mass and energy tell this fabric how to curve. The fabric tells matter and light how to move. The simplest path between events is not a flat line, but the geodesic of that fabric. Near Earth, those geodesics look close to Newton's gravity because Earth's curvature of space-time is small on human scales. Near a black hole, the curvature is strong, and paths can bend so far that light orbits or falls inward. Precision experiments, satellites, clocks on airplanes, signals from pulsars confirm these predictions. The curves are not a metaphor. They are measurements. None of this makes straight lines the enemy. They are a tool. They are great for framing a house, laying track, or drafting a diagram. The right view is to treat straightness as a local rule and curvature as the global rule. Over small regions, straight lines work well. Over large regions, or near strong gravity, or in soft materials, curves give better answers. When we match the model to the scale and the forces involved, confusion drops away. This way of thinking also helps with how we learn. We start with simple shapes because they are easy to hold in mind. Then we add detail. The sphere for Earth, the ellipse for orbits, the geodesic for curved space, the branching law for vessels, the spiral pattern for galaxies. Each step keeps what worked before in its proper range and explains the part that did not fit. The world is not trying to trick us. It is showing us the cost of using a tool beyond its range. Stand back, and the pattern is clear. Straightness belongs to plans, measurements, and small regions where forces cancel neatly. Curvature belongs to motion, growth, and fields that shift with matter and time. As you widen the view from a jet's route to a photon skimming a galaxy cluster, the picture bends more and more. What began as a tidy rule turns into a special case, which is progress, not loss. Seen through that lens, the next step follows naturally. If motion keeps revealing curvature, then space itself must have shape. That idea changes how we think about every path. In older views, space was a rigid stage, and time a separate, steady clock. In modern physics, they are one fabric, space-time. Mass and energy do not sit on that fabric without effect. They tell it how to curve. Objects do not need an invisible pull to change direction. They follow the straightest paths the fabric allows. In curved space-time, those straightest paths are not Euclid's lines. They are geodesics routes that can look curved when viewed from the outside. This view comes from general relativity, the theory Albert Einstein published in the early 1900s. It does not throw away Newton's picture. Newton's laws work well for weak gravity and ordinary speeds. They are still used every day in engineering, navigation, and mission design. What Einstein added is the reason behind the pull and the corrections that show up when gravity is strong or when clocks and rulers must be very precise. In that regime, geometry is not just a tool for drawing. Geometry is the driver. A common way to picture this is the rubber sheet model. Imagine a tight, elastic sheet. Place a heavy ball in the middle. The sheet sags. Roll a small marble nearby. It curves toward the depression. In the model, the sheet stands in for space-time, and the heavy ball stands in for a massive object, like a planet or a star. This picture is helpful for one idea. Mass changes the shape of the space around it, and other bodies follow the shape. It also has limits. Real space-time is not a two-dimensional surface, and gravity curves time as well as space. Still, for a first look, the model helps you see why objects bend without a visible cord pulling them. Evidence came early. In 1919, during a total solar eclipse, teams measured the apparent positions of stars near the sun's edge. Their light arrived, slightly shifted, because the path of that light bent as it passed through the sun's gravitational field. The measurement matched Einstein's prediction. The result did not make Newton wrong. It showed that his laws are a good approximation in many cases, and that Einstein's theory is needed when light and strong gravity are involved. Since then, many other tests have stacked up. The slow rotation of Mercury's orbit, the time delay of radio signals that pass near the sun, the behavior of binary pulsars, and the detection of gravitational waves from merging black holes and neutron stars. Each test fits the curved spacetime picture. Light itself follows geodesics. In a uniform medium and over short distances, we treat light as moving in straight lines. That works for mirrors, lenses, and everyday optics. In reality, even air can bend light a little, because air density changes light's speed. That is refraction. Over much larger distances and near heavy masses, the bending comes from curvature of space-time, not from a change in the medium. This bending is called gravitational lensing. When a massive galaxy cluster lies between us and a more distant galaxy, the cluster's gravity changes the paths of the incoming light. The background galaxy can appear stretched into an arc, multiplied into several images, or magnified. Astronomers use this lensing to map where mass is, including dark matter we cannot see directly, and to study very distant galaxies that would otherwise be too faint. Space and time belong to one structure, so when space curves, time also changes. A clock in a deeper gravitational potential runs more slowly than a clock higher up. This is gravitational time dilation. You do not notice the difference in daily life, but our tools do. GPS satellites carry precise clocks. They orbit above most of Earth's mass and move quickly, so two effects show up: special relativity, moving clocks tick slower, and general relativity, clocks farther from mass tick faster. Engineers correct for both so that positions on the ground come out right. Without those corrections, a navigation fix would drift by many meters each day. The details may seem technical, but the lesson is simple. Even time is part of the geometry. When you think about orbits with this in mind, the picture sharpens. An orbit is not a string pulling a planet around a circle. It is motion along a geodesic shaped by mass and the object's own speed. A classic thought experiment helps. Fire a projectile from a high mountain. At low speed, it lands nearby. At higher speed, it travels farther before hitting the ground. If the launch speed is high enough, the fall of the projectile matches the curve of Earth. It never hits. It falls around the planet. That is an orbit, continuous free fall that misses the surface. The International Space Station works this way. It is not hovering, it is in free fall at about 7.7 kilometers per second, around 17,000 miles per hour, always falling toward Earth, always moving sideways, fast enough to keep missing. The shapes of these paths were measured long before relativity. In the 1600s, Johannes Kepler analyzed detailed observations and found that planets move in ellipses, not perfect circles, with the Sun at one focus of each ellipse. He also found two other rules. Planets sweep out equal areas in equal times, and the squares of their orbital periods scale with the cubes of their average distances from the Sunday. Kepler did not know the cause. Later, Isaac Newton showed that a gravitational force that weakens with the square of distance, combined with his laws of motion, produces those ellipses. He also showed that other conic sections appear. If an object has more than enough speed to escape, its path can be a parabola or a hyperbola. These are open curves. The object comes in once and never returns. Comets are a clear case. Some comets follow long, stretched ellipses that bring them near the Sun and then send them far out for decades or centuries. Other bodies, like some interstellar visitors, follow hyperbolic paths and leave the solar system after one pass. Spacecraft use this range of curves on purpose. During a gravity assist, a craft dives past a planet and steals a little of the planet's orbital motion, changing the craft's speed and direction without using much fuel. The path is still a geodesic shaped by gravity, not a straight line. The mission plan chooses the entry and exit conditions to get the desired curve. Orbits are not isolated. The Moon orbits Earth. Earth orbits the Sunday. The Sun and its planets orbit the center of the Milky Way. Our galaxy moves within a larger set of galaxies bound together by gravity. Each level adds small changes called perturbations. The Moon's path wobbles because the Sun pulls on it. Earth's path changes slowly over tens of thousands of years as other planets tug at it. These are part of cycles that affect climate on long timescales. Jupiter's large mass alters the orbits of many small bodies. These effects are measurable and predictable when the system is stable, but they remind us that the simple ellipse is an ideal shape. Real paths drift, precess, and exchange energy and momentum with neighbors. If we return to the shape of space itself, the curves come in several forms. Around isolated masses like stars, space-time is curved in a way that produces orbits and bends light. Near very compact objects such as neutron stars and black holes, the curvature becomes strong. A black hole is a region where gravity is so intense that not even light can escape once it crosses a boundary called the event horizon. The surface of the star that formed it is gone. What remains is space-time curved to an extreme. Light can orbit at special radii. Time for a distant observer appears to slow for matter falling in. These are not poetic claims. They are reported by signals from X-ray binaries, by timing of pulsars, and by the shapes of gravitational waves recorded when massive compact objects merge. The curved space-time idea also explains why straight lines are good only in limited regions. Over small distances and weak fields, space looks flat. In that case, a straight line in the Euclidean sense is a good stand-in for a geodesic. This is why a carpenter's level, a laser in a classroom, or a straight road over a few miles behaves as expected. Over large distances, or near massive bodies, the differences add up. Airline routes follow great circles on the sphere of Earth because that is the geodesic of a spherical surface. Signals crossing the solar system bend slightly near the Sunday light from a galaxy billions of light years away can be lensed into arcs by the mass of a cluster. It helps to be clear about what a geodesic means. On a flat plane, the geodesic between 2 points is the usual straight line. On a sphere, the geodesic is a great circle. On a curved space-time, the geodesic depends on how both space and time are curved. The shortest or straightest path is defined by the geometry itself, not by our drawings on paper. This is why straight is not absolute. It is local, and it is tied to the shape of the surface or space-time you are using. The same thinking shows up in how materials and flows prefer curves. A pipe with a sharp corner creates turbulence and energy loss. A rounded bend keeps the flow smoother. A bone with gradual curves spreads load better than a rigid, thin bar. A bridge with an arch sends weight into the supports without a sharp stress point. These choices are not about style. They're about how forces move through matter. Nature and engineering often converge on similar shapes because the math of stability and efficiency points the same way. At smaller scales, motion looks even less like a clean line. Molecules in a gas or liquid move in constant jostle. Their paths are broken up by collisions. If you watch a tiny grain in water under a microscope, it wanders in a random way. That is Brownian motion. In quantum physics, particles behave like waves. We talk about a spread of possible positions and momenta. When you measure more precisely, you disturb the system more. The simple, thin track from point A to point B is not the best model. Instead, probability and waves guide our predictions, and results match those predictions only when we accept that smooth, single-path pictures are limited. None of this means straight lines have no place. They are efficient for design, layout, and calculation. They give us coordinates, grids, and frames. The right stance is to know where they work and where they do not. On local scales with weak gravity and little change, a straight line model is fine. On global scales, near strong masses, or in very precise timing, curvature is the right language. This mix is normal in science. Start with the simplest model that works, add detail when needed, and keep track of the domain where each model applies. There is also a useful way to link the old and the new. If you turn down the curvature in general relativity, imagine mass is small and speeds are low. The theory reduces to Newton's gravity. This is called a correspondence limit. Good new theories agree with successful old theories where the old ones have been tested. That is why engineers can use Newton's laws for building bridges, and why mission planners can choose between Newtonian or relativistic calculations, depending on the precision required. The curve appears when you zoom out or when measurements become sharp enough to reveal it. When you put these pieces together, a clear picture forms. Gravity is not a string that reaches out across space. It is the shape of space-time, set by mass and energy. Objects move by following that shape. Light bends because its path lies in a curved geometry. Time rates change with position in a gravitational field. Orbits are free-fall paths within this curved structure. The same preference for curves appears in stable flows and strong, durable designs because curves spread out loads and avoid sharp changes. Straight lines still matter as local tools, but they are not the default shape of the universe. If you expected perfect lines at every scale, this may feel like a loss. It is not. It is a refinement. We keep the simple rule where it works and replace it with better rules where it does not. In return, we gain accurate predictions of eclipses, transits, radio delays, satellite timing, gravitational waves, lensing arcs, and the slow drift of orbits. The world becomes easier to understand because we match our language to how it behaves. In practice, that means measuring carefully, choosing the right geometry, and respecting the range of each model. The result is a steady conclusion. In nature, paths are set by geometry, and the governing geometry is curved. Shift from principle to practice, and the consequences become concrete. Curved motion in space isn't laid down by rails or hidden tracks. It appears because gravity shapes space-time, and moving bodies answer to that shape. A planet needs no steering, a moon no pilot. Momentum carries them forward. Curvature turns that motion. On a trajectory screen, the sketch looks clean, yet the execution is unforgiving. A burn that runs a fraction too long, or a pointing error of tenths of a degree, can morph a tidy ellipse into an unintended re-entry or a missed flyby. Elegant flight paths balance speed, direction, and gravity, and in that balance, curves are favored. Only where gravity fades does anything like a straight line appear, and in a universe crowded with mass, that case is rare. You can frame an orbit as an agreement between two effects. Momentum would carry an object forward in a straight line. Gravity bends that motion inward. The result is continuous freefall that misses the source of gravity again and again. Seen this way, nothing needs commands once set up. The shape of space-time and the object's initial state determine the path. Precision matters because many small influences, solar radiation pressure, uneven gravity fields, the pull of nearby bodies accumulate over time. A clear example of using curvature to our advantage is the gravitational assist. A spacecraft flies near a planet, drops into its gravity well, curves around, and departs in a new direction with a new speed. No propellant is burned during the turn. The spacecraft exchanges energy and momentum with the planet. The planet loses an imperceptible amount of its orbital energy, and the craft gains exactly that amount. The idea is similar to a moving object transferring speed to a smaller object in a glancing interaction. But in space, the exchange is continuous and smooth. Engineers time the flyby, so the craft leaves along a path that meets mission goals. The same basic physics lets you redirect without capture or leave with a useful boost. This method has been essential for missions to the outer solar system. The Voyager probes used a rare alignment of the giant planets to pick up speed in a series of steps. Each flyby, Jupiter, then Saturn, and for Voyager 2, Uranus and Neptune, reshaped the path and added energy that propellant alone could not supply. The result was a tour that reached multiple worlds and then carried both craft toward interstellar space. Modern missions continue to apply the same tool because it saves mass and extends reach. The same logic applies closer to Earth. Many satellites do not use perfectly circular paths. They follow ellipses that bring them close to Earth at perigee and far at apogee. Near perigee, they move faster. Near apogee, they move slower. Mission designers choose these shapes to meet observation needs, spending more time over certain latitudes, lining up with daylight at repeat times, or matching ground station visibility. Changing an orbit is also most efficient at the lowest point, where speed is highest. Small burns there produce larger changes in the opposite side of the orbit. This is why many maneuvers are scheduled at perigee or apogee. Geostationary orbit shows how a specific curve can produce a stable view. Place a satellite above the equator at the right altitude and speed, and its orbital period equals Earth's rotation. From the ground, it appears fixed over one point on the horizon. The satellite is not still. It is moving fast in a circular path, but its motion is synchronized with the planet's spin. Communication links and weather imaging depend on this steady geometry. A straight path could not keep station. The craft would drift off the view line as Earth turned. Objects that come from the edges of the solar system illustrate longer, slower curves. Comets start far from the Sun, where their motion is set by weak gravity and remote distances. As they fall inward, they speed up and trace elongated loops. Near the Sun, heating releases gas and dust, forming a coma and tails that point away from the Sun due to solar radiation and the solar wind. After the turn, many comets head back out along the same long ellipse and return only after decades or centuries. Some cross near planets and have their paths altered by those encounters. A few gain enough energy to leave, following open curves that do not return. In each case, no engine is needed to draw the path. Mass, distance, and initial velocity are enough. Close encounters with massive planets are common shapers. Jupiter, with its large mass, can deflect small bodies by substantial angles. Some comets we see today were likely redirected long ago by Jupiter or Saturn. The change can reduce a distant loop into a path that brings the object into the inner solar system, or can fling it outward. Spacecraft can also use these giants for assists, planning flybys to reach new targets, or to save fuel. Missions aimed inward use assists as well. To approach the Sun closely, a craft must shed a large amount of the sideways speed it inherits from Earth's orbital motion. The Parker Solar Probe solves this with repeated flybys of Venus. Each pass removes a bit of the craft's orbital energy, dropping its perihelion lower. Over time, the path shrinks into an orbit that skims close to the Sun, allowing measurements of the solar corona and the solar wind at distances not reached before. The plan is careful, incremental, and relies on curves that are set by gravity rather than by long burns. When you simulate many of these paths at once, the results show arcs that cross and nest, not straight chords. Transfers between orbits often combine short burns with long coasts, using natural motion to do most of the work. Mission profiles are designed around windows when planets and moons line up so that the needed curves are available. The same planning applies to constellations of satellites near Earth. Their relative spacing is held by small corrections superimposed on long periods of coasting. The key point is that all of these motions, assists, captures, transfers, and escapes exist because gravity sets the geometry. If space were truly flat and gravity acted like a simple, uniform pull everywhere, you could still have orbits, but the fine structure of these maneuvers would not match what we observe or use. In the real solar system, gravity varies with distance and direction, and bodies interact. The effective result is a landscape of potential energy in which curves are the natural routes. Large structures in the universe follow related rules. Spiral galaxies are common, and their shapes stand out even at great distances. A typical spiral shows a central bulge, a flat disk, and arms that wind around that center. At first, you might expect the disk to smear out. Inner parts orbit faster than outer parts, so any fixed pattern should wind up tightly, yet the arms persist. The reason is that the arms are not fixed strings of stars. They are regions where the density of material is higher than average, and this pattern, called a density wave, moves through the disk. A simple analogy helps. In heavy traffic, cars bunch up in places. The clump moves along the highway, but the individual cars pass through it. In a galaxy, gas and stars move through the spiral pattern. As gas enters a density wave, it is compressed. Compression can trigger star formation. Newborn stars are bright and short-lived, so the arms look blue and vivid where formation is active. After a time, those young stars drift on, and new regions light up elsewhere along the arm. The visible spiral is the signature of where activity is higher, not a permanent chain of the same stars. Differential rotation supports the shape. The inner disk completes, orbits more quickly than the outer disk, stretching features along the direction of motion. The pattern speed of the spiral, the rate at which the density wave rotates, differs from the orbital speeds of individual stars. Where the two match, special resonances can appear, changing how gas flows, and where stars form. Bars that cross the centers of many spirals also affect the flow, feeding gas inward and shaping inner rings. None of this requires a rigid skeleton. The structure is maintained by gravity and rotation acting together on a thin, rotating mass of stars and gas. There is another part of the picture that became clear from measurements of how fast galaxies rotate. If only the visible matter were present, stars, gas, and dust, the outer regions should orbit more slowly than they do. Based on the pull from what we can see, the rotation speed should drop with distance from the center, much like planets move slower, farther from the sunday. Instead, many spiral galaxies have flat rotation curves. Beyond a certain radius, the speed stays nearly constant with distance. The simplest explanation is that there is more mass present than the light shows. We call this unseen mass dark matter. It does not emit or absorb light in the usual way, but it exerts gravity. Dark matter forms extended halos around galaxies, much larger than the bright disks and bulges. The extra mass increases the gravitational pull in the outskirts, supporting the higher speeds we measure. This added gravity also influences how spirals form and persist, how bars grow, and how gas settles into disks. In galaxy clusters, the total mass needed to hold the system together is also much larger than what visible light implies. Independent lines of evidence agree. Lensing maps of mass, motions of galaxies, hot X-ray gas held by cluster gravity, and the pattern of temperature fluctuations in the cosmic microwave background. Taken together, they point to a universe where most mass is dark. Understanding that the dominant mass is in a halo helps explain why the disk can be thin and stable while rotating quickly. The halo acts as a massive, nearly spherical container that keeps the overall gravitational field smooth. Within that field, the disk forms, rotates, and develops patterns like spirals and bars. Gas clouds move inward or outward under torques from these patterns, and star formation turns gas into stars in regions where compression is strong. Over long times, the distribution of matter changes slowly as stars age and gas is used up or replenished by inflow. Curved motion is visible at smaller scales inside galaxies, too. Stars orbit the galactic center on paths that are near circular or slightly elliptical, tilted by small angles from the disk plane. Massive clouds of gas follow similar paths, but can collide and merge, changing their speeds and shapes. These interactions lead to new star-forming regions, supernova feedback, and waves that travel through the disk. At each level, the geometry and the forces present pick out preferred curves. There is no need for hidden tracks. The rules of mass, gravity, and motion are enough. When you look at a wide field image of a spiral galaxy, the arms can appear smooth, On closer inspection, they break into knots, filaments, and arcs. Those details trace the local physics: shock fronts where gas is compressed, clusters of young stars, and lanes of dust that absorb light from behind. All of these features move along the general pattern set by the galaxy's gravity and rotation. The visual order we notice is the large-scale result of many local processes running under the same constraints. The same gravitational lensing that bends light near clusters also appears around galaxies. A massive galaxy or small group can act as a lens, slightly distorting the images of much more distant galaxies behind it. By measuring the pattern of this weak lensing across many background sources, astronomers map how mass is distributed, including the dark matter halo. Strong lensing, where arcs and multiple images are obvious, provides even tighter constraints on mass in the central regions. These measurements match the picture drawn from rotation curves. Significant mass extends beyond the light. All of this points in one direction. Curves are not a special effect layered on top of a flat world. They are the natural outcome when mass and motion interact in a shaped spacetime. Spacecraft navigation, satellite operations, comet paths, and the structure of galaxies all reflect this. Where gravity is stronger, or where distances are larger, the preference for curved paths is more obvious. Where scales are small and fields are weak, straight lines serve as good approximations. Recognizing which case you are in is the practical skill. With that in view, the next step is clear. Spiral structure, rotation speeds that stay high in the outskirts, and lensing patterns all point to more mass than we can see. That mass shapes the curves we measure on galactic scales. To understand why these systems look the way they do, and why their motions remain stable over long times, we add the missing ingredient: dark matter. Most of a galaxy's mass is not the bright stars and glowing gas. This unseen matter does not shine, absorb, or stick to normal matter through electric forces. It reveals itself only through gravity. Its pull holds stars in their paths. When astronomers measure how fast the outer parts of spirals turn, the speeds stay almost constant, with distance a flat rotation curve. If only visible matter were present, those outer stars should slow and some would drift away. They do not. The simplest fix is extra mass spread in a large, roughly spherical halo around the galaxy. We call it dark matter. It outweighs the visible material by several times, gives the disk the grip it needs, and matches lensing maps that trace mass without relying on light. This hidden halo acts like a stabilizing frame. It deepens the galaxy's overall gravity without adding bright glare to the disk. The result is a system that can spin quickly and still hold together. The bright spiral arms, the thin starry disk, and the faint outer gas all move inside this larger, darker mass. Gravity from the halo supports the high speeds we record, especially far from the center, and reduces how easily the disk would be pulled apart by small disturbances. In many different galaxies, the same story repeats. Light shows only part of the mass. Gravity adds the rest. Spiral galaxies are common because rotation and gravity work together on a flat disk of stars and gas. The arms are not rigid structures. They are patterns where material crowds for a time. As gas enters a spiral arm, pressure rises and star formation turns on. Hot, young stars shine blue and make the arm easy to see. Over time, the stars drift onward and new bright patches form elsewhere along the arm. The spiral is a wave of higher density moving through the disk, not a permanent chain. The dark matter halo helps this pattern last by keeping the disk from flying apart and by shaping the speed curve so the arms do not wind into an unrecognizable tangle too quickly. The spiral shape is not only a galaxy story. It appears in rotating systems across nature, because rotation plus inward or outward flow tends to produce curves. On Earth, hurricanes form over warm oceans, where rising moist air feeds a low-pressure center. The Coriolis effect, a deflection caused by Earth's rotation, turns that inflow into a rotating storm. Bands of clouds and rain wrap around a calmer eye. Energy moves from the warm ocean into the atmosphere, and the spiral pattern shows how the air converges and rotates. It is not a galaxy, but the same idea applies. A rotating system, a gradient that drives flow, and a shape that organizes motion. Ocean gyres are large, slow swirls in the sea. Wind patterns, Earth's rotation, and the shapes of continents guide surface currents into broad loops. These loops move heat and nutrients around the planet. The path of a water parcel is curved by the balance of forces at play, wind stress, pressure changes, and the Coriolis effect. The details differ from a galaxy, but the outcome is familiar. A stable, curved route that moves material efficiently over long distances. Spirals appear in small places as well. The curl of a snail shell, the pattern of seeds in a sunflower head, and even the swirl in a cup of coffee echo the same theme. The common thread is growth or flow that scales while keeping order. A special kind of curve, the logarithmic spiral, has a property that helps. As it expands, its shape is self-similar. That means it keeps its overall form while growing larger. In biology, this is useful because a structure can scale up without needing a new plan at each step. A nautilus shell shows this clearly. The animal adds new chambers as it grows, and each chamber keeps a similar proportion to the last. The result is a spiral that looks the same whether you measure near the center or near the edge. This is efficient for building and for buoyancy control. There is no blueprint recalculation needed. The growth rule is simple and produces a consistent form. The shell is not a perfect mathematical spiral if you measure it closely, but it follows the idea well enough to serve the animal's needs. Horns in some mammals also use spiral growth. Rams, goats, and antelopes grow horns that curve and twist instead of sticking straight out. A straight, long horn would be easy to break and would shift weight far from the head. A coiled horn spreads stress across the curve and keeps the center of mass close to the skull. That makes impacts less damaging and motion more stable. Growth along a spiral path can also keep the horn from interfering with the animal's field of view or balance. Plants use spirals to pack parts efficiently. Look closely at a pine cone, a sunflower, or a pineapple, and you will see two sets of spirals crossing in opposite directions. Count the number of spirals in one direction and in the other. The counts often match neighboring Fibonacci numbers, such as 8 and 13, or 13 and 21. The Fibonacci sequence starts 0, 1, then each new number is the sum of the previous two. Ratios of neighboring Fibonacci numbers approach a value known as the golden ratio. Placing seeds or scales according to angles related to this ratio spreads them evenly around a circle. The pattern reduces overlap and fills area efficiently. Plants are not doing math. Variants that pack well tend to capture light better or place seeds with less waste, so they endure. This kind of packing solution appears in leaf arrangements on stems called phyllotaxis. Leaves spaced by a golden angle fraction of a turn avoid shading each other. The spiral arises from local growth rules and competition for space. not from a top-down design. Over generations, growth patterns that deliver more light and less overlap win. What we see as a neat spiral is a result of many small decisions made by cells dividing and expanding under chemical signals and physical constraints. Biology also uses spirals for function, not just packing. The cochlea in the inner ear is a spiral tube. Sound waves enter and travel along it. Because of how the membrane and fluids are built, different parts respond to different frequencies, high near the base, low near the tip. The spiral layout fits a long sensing surface into a compact volume and helps separate frequencies in an orderly way that makes hearing more efficient in a small space. Even our skin shows looped and spiral patterns. Fingerprints form from growth and stress patterns in the skin of the fetus. Whorls and loops provide grip and sensitivity. The swirl at the back of the head, called a hair whorl, arises from the way skin and hair follicles grow and align. These are not exact logarithmic spirals, but the recurrence of curves is striking. When growth spreads from a center or follows a slight rotation, spirals appear naturally. At the molecular level, DNA forms a double helix, a pair of strands winding around a shared axis. It is not a planar spiral like a shell, but it is still a repeating, curved structure defined by chemical bonds and geometry. The helical shape makes it stable and compact, yet accessible for copying and reading. Proteins also coil into helices as one of their common shapes, again because the geometry of bonds and the need for compact, stable forms favor them. The Fibonacci pattern is a tool in this story, but it is not a law that rules all spirals. Real organisms show variation. Counts can differ, angles shift, weather or injury can warp growth. This variation does not break the rule. It shows that the underlying reason is practical: efficient packing, stable growth, and balanced force. Evolution chooses what works better, not what fits a clean formula. The formulas describe trends because the same constraints appear again and again. Returning to galaxies, the spiral is also a practical shape. It is a visible guide to where gas is compressed and where stars are forming. It moves material inward over time, through torques twisting forces from bars and arms, feeding central regions, and sometimes growing a central black hole. It redistributes angular momentum, allowing gas in the outer disk to move outward, while other gas loses angular momentum and drifts inward. The pattern is not decoration. It is part of how a galaxy evolves. Not all galaxies are spirals. Some are ellipticals, smoother and rounder, with stars on orbits that point in many directions. Others are irregulars, with no clear shape. Spirals tend to be where there is still plenty of cold gas to make new stars, and a disk to organize that gas. Ellipticals often form after mergers or through processes that heat or remove gas, reducing the ability to make new stars and blurring any disk pattern. Lenticular galaxies sit in between, with disks but little ongoing star formation and weak spiral structure. The variety shows that spiral patterns need specific conditions to thrive. The dark matter halo affects these outcomes. A massive extended halo can stabilize a disk against some disturbances while still allowing bars and spirals to grow. It sets the speed scale at large radii and helps retain gas against stripping by neighbors, all by a cluster's hot gas. Lensing observations where background galaxies are distorted by the mass of a foreground galaxy or cluster map. This hidden mass, motions of stars and gas confirm it. The cosmic microwave background adds support by showing the early universe pattern that later grew into halos and galaxies. Many unrelated measurements point to the same picture. Most mass is dark, and it shapes the curves we see. The spiral pattern is also efficient for star formation economics. Gas clouds that enter an arm are shocked gently and compressed to densities where they can cool and collapse. Feedback from young stars, radiation, winds, and supernovae then stirs and heats the gas, preventing runaway collapse of everything at once. The result is a cycle. Gas collects, forms stars, is stirred and spread, and then collects again as it meets the next arm. The shape organizes this cycle across the disk. On the smallest timescales, individual stars and clouds follow near circular orbits set by the galaxy's mass. On longer timescales, the pattern of arms, bars, and rings moves through those orbits. Material flows relative to the pattern. Over hundreds of millions of years, the overall picture remains recognizable because the processes reinforce the same geometry. When something disturbs the disk, a close pass by another galaxy, for example, new waves can form, new bars can grow, or arms can become more open or more tightly wound. Still, the preference for curved, organized motion remains. Across all these cases, galaxies, storms, shells, seeds, and senses, the same logic appears. Curves distribute stress more evenly than sharp corners. Spirals let growth scale without constant redesign. Rotation plus inward or outward flow tends to produce arms or bands that curve. Systems that must pack parts into round areas often use spiral layouts to avoid waste. None of this requires perfect math in nature. It requires rules that favor stability and efficiency under real constraints. The idea that dark matter anchors the outer parts of galaxies fits seamlessly into this broader view. A spiral disk can rotate fast and remain thin because the halo provides gravity without adding drag or brightness. The arms can persist as patterns that move through the disk. The rotation curve can stay flat far out where there are few bright stars. And when we measure lensing, gas temperatures, and the motions of satellites around galaxies, the same answer appears. There is more mass than meets the eye, and it shapes the paths we trace. Once you see the connection, the spiral stops being ornament and becomes a working solution that physics reuses. It appears whenever matter must move, grow, or pack efficiently under rotation and gentle forces. It explains why galaxies hold their shape, why storms organize, why plants place leaves and seeds the way they do, and why strong structures avoid brittleness. The curve isn't a flourish added to nature. It's what forces produce when systems seek stability. You don't have to look far to watch that rule at work. Your own body follows the same blueprint. Beneath skin and muscle, form serves flow. Arteries bend like slow rivers. Veins loop toward the heart, and airways branch and rebranch into a tree that reaches deep into the lungs. The layout is not random. It's a network tuned to move fluids and gases with minimal loss and minimal harm. Curves steady motion, sharp angles invite trouble. Fluid dynamics, the study of how liquids and gases move, shows two broad kinds of flow. Laminar flow is smooth and layered. The fluid slides in sheets, with the fastest layer near the center of a tube and slower layers near the wall. Turbulent flow is chaotic. Swirls and eddies appear. Pressure jumps up and down. In delicate systems, turbulence can scrape and stress the walls, wasting energy and risking harm. That is why engineers soften pipe turns and add gentle elbows. The body follows the same rule. A curved vessel eases pressure, changes, and helps blood stay laminar over a wide range of speeds. Each heartbeat pushes a strong pulse into the aorta. If the path were perfectly straight, the pulse would slam into the next segment and rebound, building sharp waves and extra stress. The aorta forms an arch. That curve changes direction smoothly and spreads the impulse into a controlled bend toward the chest and abdomen. Downstream, major branches peel off at gentle angles rather than 90 degrees. The design limits sudden separations in the flow that would otherwise seed turbulence. Over many years and billions of heartbeats, this reduces wear on the inner lining of vessels. Smooth flow is not only safer, it is efficient. A curved path lets blood reach distant organs without the heart having to raise pressure to damaging levels. Vessel walls add another layer of control. The inner surface is lined by endothelial cells. These cells sense the friction of moving blood, a quantity called shear stress. In steady, laminar conditions, they release signals that keep vessels relaxed and healthy. When flow turns irregular and swirly, the cells detect the change and may become inflamed. The body can then remodel the vessel, widening or narrowing sections, growing side roots, or strengthening the wall. The geometry is living. It adjusts to preserve smooth motion. The respiratory system uses the same ideas with air. The trachea divides into bronchi, which divide into smaller bronchioles, which end in tiny sacs called alveoli. At each split, tube diameters shrink, but the total cross-section grows. The branching is a kind of fractal, a pattern that repeats its basic shape at smaller and smaller scales. This layout packs a huge exchange surface into a small volume. When fully expanded, the lungs present on the order of 700 square feet of area for oxygen and carbon dioxide to trade places about the floor space of a small apartment folded into the chest. Curves in the airways also help set the right speed. Air moves quickly in the larger tubes, then slows as it spreads into many tiny passages. Slower flow near the alveoli gives gases more time to cross the thin barrier into blood. If air rushed too fast all the way down, exchange would be poor. If it were forced through sharp corners, local turbulence would grow and could irritate tissue. The tapering and bending of the tree solve both problems at once. Large volume at the end, smooth guidance along the way. Curves add strength too. A straight column under sideways force can buckle with little warning. A gradual arc distributes stress over a wider region and changes shape without sudden failure. Architects have known this for centuries. Arches and bridges pass load to the ground smoothly. The body takes the same path. Arterial walls stretch and recoil with each beat. Bronchi withstand pressure swings as we inhale and exhale. Rounded shapes let them flex and return without tearing. The scale of the circulatory network is easy to forget. The heart beats more than 100,000 times per day. Blood travels through a web of arteries, arterioles, capillaries, venules, and veins, whose combined length reaches tens of thousands of miles. A rigid, sharp-edged layout could not survive this workload. A curved, elastic one can, and it does so quietly. Capillaries weave between cells rather than drawing straight lines. Their winding roots shorten the maximum distance from any cell to a source of oxygen and nutrients. That redundancy keeps tissue alive. If one tiny branch is blocked, nearby paths can take over the load. Evolution favors systems that move resources at low cost. Fish, birds, mammals, and many other animals show looping, branching vessels tuned to their size and activity. The details differ, but the theme repeats. Keep flows laminar when possible. Use arcs to steer pressure and branch to reach more area with less material. Even the local repair rules support this. When flow is steady, vessel walls stay smooth. When a region sees irregular flow, signaling changes, and the structure adapts to bring conditions back toward steady. The network maintains itself because shape and function feed back on each other. The nervous system and lymphatic system also rely on branching geometry. Nerve fibers split to reach wide fields while keeping conduction efficient. Lymphatic vessels gather fluid from tissue in fine channels and carry it back to larger trunks. Again, we see curves, tapering, and repeated splits, not grid lines and hard corners. The design is less about straight distance and more about balanced delivery and collection. The same branching logic appears across the landscape. A tree grows a trunk, then major branches, then smaller branches and twigs. The pattern spreads weight and catches light. Thick branches take bending loads. Thin branches place leaves where they can absorb sun and move air. The tree must also shed forces from wind without snapping. Curves help by letting branches twist and sway. Each fork spreads stress into two paths and keeps leverage under control. The overall shape covers a large volume with minimal material. Rivers follow a related plan. High on a slope, tiny rills join to form small streams. Streams join to form larger reaches. The result is a drainage basin, a network that collects water from wide areas and funnels it toward the sea. Seen from above, the map looks like a tree laid on its side. The pattern is called dendritic, from the Greek for tree. Gravity pulls the water downhill, but the exact routes reflect rock types, soil, and previous channels. Over time, channels that carry water well deepen and persist. Those that do not fill and fade. The network is efficient at collecting and distributing flow because it branches many times. Lightning reveals branching on a different timescale. Charge builds in a cloud and seeks a path to reduce the imbalance. The air does not conduct well, so the discharge grows in short steps, testing multiple directions. Branches that hit dead ends stop. Branches that find easier air continue. When a path links cloud and ground, the main bright stroke races along that temporary channel. The jagged shape is not random. It is the record of many small choices guided by electrical resistance and local fields. The common look among trees, rivers, and lightning is an example of self-similar structure. A small part of the network resembles the whole. That is what is meant by a fractal, a pattern that repeats at different scales. The rules are simple branch to cover area, split to reduce load, seek the easiest path, and the result is a shape that balances reach, strength, and cost. Branching reduces the amount of material needed to fill space. It also creates multiple routes, adding resilience. Inside the chest, the bronchial tree branches roughly 24 times from the trachea to the alveoli. Each split reduces the size of the tubes but increases the sum of their cross-sections. That shift from few large pipes to many small ones is why air slows smoothly before it meets the exchange surface. Blood vessels behave similarly, as arteries branch into arterioles and then into dense capillary beds. The slow flow in capillaries allows time for exchange with tissue. The network then collects the blood through venules and veins and returns it to the heart. The same plan, branch to deliver, branch to collect, solves a broad class of problems with one geometry. Even at the scale of single organs, curves and branches work together. In the kidney, tiny filters called glomeruli receive blood through arterioles that divide and loop. The layout sets pressure and flow to filter waste while keeping cells safe. In the liver, plates of cells and sinusoids spread blood across a large surface for metabolism. The layouts are not perfect spirals or perfect trees, but they use the same tools: bends to soften forces and branches to reach area. What seems like complexity is often the repeated use of a few rules under different constraints. Avoid sudden changes in direction that would cause turbulence. Spread stress with curves rather than corners. Increase surface area by splitting and tapering. Allow many small roots instead of one large one to add resilience. Let local feedback like endothelial sensing of shear tune the shape over time. The result is a map of curves that fits the job. The mathematics behind these patterns can be deep, but the working ideas are plain. Curves guard against sharp stress. Laminar flow saves energy and protects surfaces. Branching reaches space efficiently and adds backup paths. Self-similar forms make it easy to scale up or down without inventing a new design at each step. The same handful of principles shape arteries, airways, trees, rivers, and bolts of lightning, because the same goals appear: move something, spread something, collect something, and do it with minimal cost and damage. You can see the trade-offs by imagining bad designs. A vascular system made of long, straight pipes with hard 90-degree turns would waste energy at every corner and damage the lining. A lung with a few big chambers and no branching would not have enough surface for gas exchange. A river forced into a straight channel would erode its bed quickly and flood more often because it could not spread energy across bends and side channels. Lightning confined to one narrow track would have trouble finding ground through real, messy air. In each case, the graceful plan fails, and the system either breaks or consumes too much energy. Because living systems grow and repair over time, the shapes you carry are not fixed drawings. Vessel diameters can change. New tiny branches can form. Airways can remodel around chronic irritation or relax when the trigger is removed. Bone reshapes along stress lines. The network updates itself using local rules and slow feedback. This is why health habits matter. Conditions that disturb flow: high blood pressure, smoking, long periods of high blood sugar can push vessels towards states where turbulence and inflammation are more common. Remove the triggers, and some of the geometry can shift back towards smoother function. Straight lines are still useful tools in planning and measurement. Surgeons use rulers, radiologists use grids, but the body that those tools examine is built mostly on curves, because curves solve the physical problems that living systems face. The same is true in the broader world. Trees, rivers, and lightning do not copy each other. They converge on similar branch and curve shapes because those shapes meet the demands placed on them. The idea scales up to cities and technology. Road networks that mix gentle arcs with branching side streets spread traffic better than rigid squares everywhere. Data networks send information along many paths rather than one, adding resilience against failure. Ventilation systems in buildings branch and curve to reach rooms without noise or waste. These are human echoes of the same physics. Move resources smoothly, share load, and keep options open. The picture that emerges is consistent. Where fluids and forces matter, curves and branches dominate. They make motion smoother, spread stress, and cover space efficiently. They appear in bodies and landscapes for the same reasons they appear in galaxies and storms. They are the shapes that work under real conditions, with limited energy and changing demands. Coral reefs, fungi, and neurons grow with the same quiet logic. Each faces the problem of reaching far while using limited resources. Reefs extend in branching corals to catch light and food from moving water. Fungi send thin threads called hyphae through soil or wood, splitting and looping to explore, absorb, and share nutrients. Neurons grow axons and dendrites that branch to contact many partners while keeping signal paths short. The materials differ: calcium carbonate, chitin, living membranes, but the geometry repeats because the goals repeat: expand, connect, distribute. The branches do not split at random. Many systems follow rules that save energy and material. In trees, the sizes of branches often scale so that the total cross-section of the daughters roughly matches the parent. This helps keep flow speeds and stresses in a safe range. In rivers, tributaries join with typical spacings and angles that spread erosion and smooth the delivery of water and sediment. In fungal networks, links are added or cut back as resources change, balancing the cost of building threads against the benefit of reaching new food. Even lightning, which moves fast and seems wild, follows statistical patterns that models can reproduce by letting a discharge seek lower resistance while paying a cost to create new path. These rules often sit between competing needs. A tree wants reach but must avoid heavy, breakable limbs. A river wants quick drainage but must avoid tearing up its banks. A neuron wants fast, reliable signaling but must minimize the energy used to grow and maintain long wires. Solutions land in the middle: enough branching for coverage, enough curve for strength, enough irregularity to avoid failure points. Straight, even spacing would look tidy, but it would be fragile. Nature uses small deviations, slightly uneven angles, gentle bends, backup links to gain resilience. Redundancy is built in. If one coral branch breaks, light still reaches many others. If a fungal thread is cut, nutrients can route around through loops. If a small river dries, nearby channels pick up the flow. The same is true in neural circuits. Multiple paths and overlapping fields make function less dependent on a single connection. This is not waste. It is insurance at low cost, because branching delivers many routes for little extra material. Human systems borrow from this geometry. Power grids radiate from sources and then mesh to allow rerouting. Road networks mix main arteries with smaller streets that branch and reconnect. The internet links hubs with many paths so packets can flow around a fault. Where we differ is our taste for straight lines and sharp corners. We like symmetry and clean layouts. Nature accepts slight irregularity because it prevents synchronized failure. A little variation in angles and lengths spreads load and helps the whole system adapt. Patterns like these also affect how we feel. People often find fractal forms, shapes that repeat at different scales, calming. Forest canopies, river deltas, and cloud edges fall into ranges of complexity our brains recognize easily. The effect is not a mystery story. It is a practical match between the visual system and common structures in the environment. When a scene contains familiar scaling, the brain spends less energy guessing what comes next. The same preference for curves and branches shows up in optics, where light moves through materials and fields. Light is fast, about 300,000 kilometers per second in a vacuum, but it is not stubborn. It follows the path available. When it enters a new medium, its speed changes, and with that change, the direction shifts. This bending is refraction. You can see it by putting a straw into a glass of water. The straw appears bent at the surface because light from the submerged part takes a different path to your eye than light from the part in air. The effect is not a trick. It is geometry obeying a rule. the path light takes minimizes travel time given the local speed in each medium. We use refraction on purpose. Eyeglass lenses are curved to bend incoming rays so they focus on the retina. A convex lens gathers light to a point. A concave lens spreads light out. Cameras and telescopes stack lenses to correct distortions and sharpen images. The curves of the glass decide where rays meet. If the curve is wrong for your eye, the focus falls in front of or behind the retina, and the scene looks blurred. Adjust the curvature, and the image snaps into place. Air also acts as a lens because its density changes with temperature and pressure. On a hot day, air near the road is warmer and thinner than the air above. Light passing through layers of different density bends upward, and your brain interprets the bent rays as a reflection from a patch of water that is not there. That is an inferior mirage. In cold regions or over ice, the layering can invert, bending light downward. A distant ship can appear, lifted above the horizon or even doubled. These superior mirages are not a failure of vision. They are a record of light choosing a faster route through a layered medium. Rainbows are another clean case. Sunlight enters raindrops, refracts, reflects off the back, and refracts again as it leaves. Each color bends by a slightly different amount because its speed in water differs. The light that reaches your eye from many drops makes an arc centered on the point opposite the sunday. For red light, the angle is about 42 degrees. For violet, it is a bit less. The result is a colored band with red on the outside and violet on the inside. If the geometry is right and the rain is below you, such as from a plane, you can see a full circle. Halos around the sun or moon form when light refracts through ice crystals high in the atmosphere. The common 22-degree halo arises because hexagonal crystals bend light by a characteristic angle. Again, no one droplet or crystal chooses a curve. The distribution of paths and angles produces the arc. Shadows reveal curvature in a different way. The sun is not a point. Light arrives from a disk, so the edge of a shadow has a soft zone called the penumbra, where part of the light is blocked and part is not. During a solar or lunar eclipse, the round shape of the bodies creates curved edges and smooth gradients. The geometry of circles and spheres shows itself in the way light is partly cut off across space. Gravity bends light too, but for a different reason. According to general relativity, mass and energy curve space-time, and light follows the straightest possible path in that curved geometry. Near a galaxy or a cluster of galaxies, the path can bend enough to stretch the image of a more distant object into an arc, or to produce multiple images. When the alignment is close to perfect, a ring can appear, often called an Einstein ring. These arcs and rings are more than striking pictures. They let astronomers measure mass that would otherwise be invisible. By modeling the distortion, we infer how much matter sits in the lensing object and how it is distributed, including dark matter that does not emit light. Gravitational lensing comes in strong and weak forms. Strong lensing creates obvious arcs and multiple images. Weak lensing is subtle. It slightly shears the shapes of many background galaxies in the same general direction. By averaging over a large field, we map the foreground mass. These methods confirm that galaxies and clusters carry far more mass than their stars and gas account for. Light is a messenger, and the curves in its path carry information about the space it crossed. Mirages, rainbows, halos, and lensing share one idea. Light respects the environment it moves through. In glass or water, the index of refraction, the factor that tells how much light slows, sets the bend. In air, temperature and density gradients do. In gravity, the distribution of mass does. Even within your eye, the cornea and lens, both curved, bend light to form a sharp image. If either surface is shaped incorrectly, or if its flexibility changes with age, focusing suffers. The act of seeing depends on controlled curvature. Light also spreads and overlaps. When waves add, they can interfere, making bright and dark bands. This happens in thin films on soap bubbles or oil slicks. Colors shift because the path lengths differ by small amounts across the film, changing how colors add or cancel. A straight, single-ray picture cannot capture that behavior. Acknowledging the wave nature of light explains the pattern with no extra stories. If you combine all these optical cases with the branching systems we see in biology and landscapes, a broad theme emerges. Curves and splits are not decorations, they are solutions. Branching lets systems reach many points with little material and adds backup routes. Curves keep flows smooth, reduce sharp stresses, and fit long paths into compact spaces. In optics, curved surfaces guide rays to where they need to go. In space, curved spacetime guides light and orbits. The same preferences appear because the same constraints move. Focus, spread, connect, survive, appear at many scales. This does not mean nature seeks perfect mathematical forms. Coral branches grow where currents and light make growth favorable, and they break in storms. Fungal networks fill some soils and avoid others. Neurons prune connections that are not used and reinforce those that are. River channels migrate. Lightning paths differ from storm to storm. The rules are local and adaptive, but when you zoom out, the averages line up with simple scaling laws. That is why researchers can measure angle distributions in branches, stream spacings in basins, or statistical properties of lightning, and find regularity among differences. Designers have learned to lean on these lessons. Medical stents aim to keep curvature and flow laminar. City planners mix arterial roads with branching side streets and roundabouts to prevent sharp bottlenecks. Antenna arrays and sensor networks use branching layouts to cover area with minimal cable. Graphics algorithms draw fractal trees and terrains with a few repeated rules to create scenes that feel natural because they share the same scale patterns the eye expects. Light, for all its speed, behaves in line with the same practical logic. It bends where bending leads to faster or permitted travel, splits into colors where materials allow it, spreads or tightens as shapes dictate, and curves through gravity, where mass bends space-time. The path is not a stubborn line, it is a response to the setting. Lenses, mirages, halos, rainbows, and gravitational arcs are the visible record of that response. Vision itself is built on it, because focusing a scene onto a thin layer of receptors requires precise curvature and careful control of paths. When the curves are right, images are crisp and information flows with little loss. When the curves are wrong, effort rises and clarity drops. Across coral heads and forests, fungal webs and city pipes, raindrops and galaxy clusters, the same message keeps appearing. Systems that move things water, air, charge, light, nutrients, information work best when they branch to reach and curve to guide. The details change with scale and material, but the geometry stays familiar. Curves prevent waste and damage. Branches cover ground. Scaling laws keep costs in check. What looks complex resolves into a small set of rules that play out wherever there is a need to deliver, collect, or focus. Light does not travel through a world that is neat and even. Air has layers, dust and droplets come and go. Gravity varies from place to place. Because of that, a single sunbeam can change direction many times before it reaches you. It bends a little in the atmosphere, scatters from tiny particles, bends again inside a raindrop, splits into colors, then bends one last time through the curved surfaces in your eye. What looks like a straight ray is really a chain of small course corrections set by the environment. Those small shifts create rainbows, halos, sundogs, mirages, and the gentle reddening of sunsets. They also let us see distant galaxies stretched into arcs by mass we cannot otherwise detect. The lesson is simple. Light is faithful to geometry. It follows the best path allowed by the medium and the gravity it meets. The same geometric rule shapes travel on Earth. Stretch a string from New York to Tokyo across a globe. The tight string bows toward the Arctic. That arc is the shortest route on a sphere. It is a great circle. On a flat map, the path looks like a detour because a sphere cannot be flattened without distortion. Aircraft follow great circles to save time and fuel. Subsea cables do the same when planners pick routes. Migrating birds take curved tracks as well, in part because winds and the Coriolis effect steer them, but also because straight on a globe means curved to a map reader. We grow up with flat rectangles on walls, so our intuition fights this. Map projections fix some things and break others. The Mercator projection keeps compass bearings as straight lines, which helped sailors, but it enlarges areas near the poles. Greenland looks huge next to Africa, even though Africa is more than 14 times larger. Other projections trade differently. The Robinson softens extremes to give a better sense of size. The Winkle tripole balances area, shape, and direction. The Good Homolocene cuts the oceans so continents keep their areas more faithfully. None are perfect, because no flat sheet can keep all distances, shapes, and areas true at once. Knowing what a map preserves helps you read it without being misled. Curvature matters in surveying and construction. If you shine a laser over a long, level stretch and hold it perfectly straight, the ground falls away under the beam because Earth is round. The drop is about 8 inches over the first mile and grows roughly with the square of distance. Engineers building long pipelines, rail lines, or tunnels account for this. They also account for refraction in the air near the ground, which can bend light slightly and change apparent levels. Small corrections add up when projects span many miles. Curvature also explains ordinary sights. Ships disappear hull first because their lower parts dip below the horizon first. From higher ground, the horizon lies farther away, and sunset comes later because your view extends over more of the curve. Astronauts in low Earth orbit see a thin blue shell around a round planet, day and night, separated by a soft edge. Even the buildings in a city are not truly parallel at the top. Each one is built to be vertical, which means each one points toward Earth's center. Extend their axes, and they meet far below your feet. We draw straight property lines and right-angled streets, but the reference surface under all of that is a curve. Finding shortest paths on curved surfaces leads to the idea of a geodesic. On a plane, a geodesic is an ordinary straight line. On a sphere, a geodesic is a great circle. The path looks curved in flat drawings because the drawing is distorted. This does not just matter for aircraft and ships. GPS receivers compute positions using spherical and ellipsoidal geometry. Long-haul fiber routes, polar flights, And even the layout of weather satellite scan lines depend on the same math. What looks crooked on paper is often correct in space. Time also follows geometry. For a long time, we treated time as uniform, the same everywhere. General relativity ties time to gravity and motion. Where gravity is stronger, clocks tick more slowly. Where an object moves quickly, its clock ticks more slowly compared with a slower one. These are not guesses, they are measured. Put one atomic clock at sea level and another on a high mountain. After enough time, the higher clock will show a slightly larger reading. The difference is tiny, but precise tools can see it. Fly a clock on a jet and compare it to a clock on the ground. Both gravity and speed leave their marks. Global positioning shows how practical these effects are. GPS satellites orbit about 20,000 kilometers above Earth and carry very stable clocks. Your phone listens to several at once, notes the timestamps, and computes how long each signal took to arrive. From those travel times, it solves for your position. The catch is that the satellite clocks do not tick at the same rate as a clock on Earth's surface. Special relativity says the moving satellite clocks run slow. General relativity says the clocks high above the bulk of Earth's mass run fast. The net is that satellite clocks tick faster than ground clocks by tens of microseconds per day, about 38 microseconds. Left uncorrected, that would put positions off by kilometers within a day. Engineers program the satellites with offsets and keep them synchronized so the system stays accurate. Navigation systems also correct for how signals bend in the ionosphere and troposphere. Free electrons in the ionosphere delay radio waves in a way that depends on frequency. Water vapor and temperature layers in the lower atmosphere bend paths slightly. Models and dual-frequency tricks remove most of these errors. Again, light and radio do not insist on straight lines. They take the fastest allowed paths through a changing medium, and we must account for that. Back on the ground, even simple sightlines carry the same message. Surveyors use the concept of level, which follows a surface of constant gravitational potential. That surface is not an exact sphere. Mass variations in Earth make small bumps and dips in the gravity field. The geoid Earth's mean sea level surface, extended under the continents, captures this shape. Modern instruments tie measurements to the geoid to get heights that match how water would actually flow. A laser may point straight, but a level line bends to follow gravity. Spherical geometry shows up in daily planning more than we notice. Airlines publish flight maps with apparent arcs. Long road tunnels are engineered with a slight upward curve in the middle, not to trick the eye, but because level follows the planet. Long bridges include expansion joints and slight arches for strength and drainage, but survey control lines that anchor them still point toward the center of Earth. Even sports satellites that relay broadcasts from geostationary orbit cluster above the equator at specific longitudes, spaced by angles, not by miles, because the sky, as seen from Earth, is an angular dome. Once you accept that both light and distance follow the rules of the surface or space-time they inhabit, apparent puzzles dissolve. The odd arc on the flight tracker is the minimum distance path. The bent straw is the minimum time path through air and water. The late sunset at altitude is a longer line of sight over a round edge. The drifting GPS would be nonsense unless we adjusted for how time flows at speed and in weaker gravity. None of this is exotic. It is the normal outcome when a world has shape and when signals are fast, but not infinite. The same logic scales up. Around massive objects, space-time curves enough to bend light from far behind. That bending produces multiple images, rings, and arcs that let us weigh galaxies and clusters. Inside the solar system, light passing near the Sun arrives a bit late because the path is longer in curved spacetime. Radio links to spacecraft must account for this Shapiro delay. Clocks on satellites must be trimmed so that your phone can place you within meters. Each case is one more proof that straight lines and steady ticks are local conveniences, not global truths. Even the way we learn mirrors this. We start with flat maps and straight rulers because they are easy to grasp. Then we add great circles, projections, and the geoid. We start with uniform time because it matches our senses. Then we add the way gravity and motion change rates by minute amounts. We start with light as straight rays in air. Then we add refraction, scattering, and lensing. Each step is a correction that keeps earlier tools where they work and replaces them where they do not. The payoffs are everywhere. Flights plan better routes, survey lines meet where they should, telescopes measure mass that does not shine, phones guide cars through city streets, weather models trace light and radio paths through layers of air. Spacecraft use bent radio links and curved gravity wells to navigate. None of these would work with a flat, rigid picture. All of them work when we let geometry lead. Seen plainly, the rule is consistent. On curved surfaces, the shortest path is a geodesic, and it looks curved on a flat map. In changing media, light bends to keep travel time minimal, and we can predict how, using the index of refraction. In gravity, clocks change rate with height and speed, and we can predict how using relativity. When we follow these rules, odd-looking routes, bent beams, and shifted seconds stop being odd. They become the expected shape of motion and time in a real, uneven world. If those tiny time shifts in satellites were ignored, your phone would place you miles from where you are. The fix is built into the system. Engineers program the satellites and receivers to apply relativity from the start. Every time a map app finds your location, the software is using corrections from Einstein's equations so the clock signals line up. Modern navigation works because we accept that time rates change with height and speed. The change grows stronger near very massive objects. Where gravity is intense, time runs slower. Near a black hole, the effect becomes extreme. If someone orbited close to the event horizon, the boundary beyond which light cannot escape, and managed not to fall in, their time would crawl compared with someone far away. An hour for the close observer could match years for the distant one. This sounds like fiction, but it is a direct result of general relativity and fits with the way gravity shifts light and clocks in many tested settings. The lesson is that time is local. There is no single universal tick that everything follows. Each place and motion sets its own pace, tied to the local gravity and speed. In daily life, we do not notice the differences because most of us live at similar elevations and move at modest speeds. Step outside that range to mountaintops, to orbit, or near compact objects, and the offsets appear. They start tiny, then grow with mass and motion. Space and time also move together. In relativity, they form one fabric, space-time. Move fast through space, and you move less through time. Sit still near heavy mass, and you move more slowly through time. Each point has a tempo set by those conditions. Gravity does not only bend paths, it changes how events are spaced in time. The idea can feel strange, and even Einstein was cautious about the human picture it gives. But the math is consistent, and the measurements agree. This link between time and space is not a word game. It shapes how we measure the world. When we talk about the geometry of the universe, we are talking about the allowed paths for matter and light, and about the time each path takes. The two cannot be separated. Bending one changes the other. Mountain clocks tick a bit faster than sea level clocks. Signals sent past the sun arrive a bit later than they would in flat space-time, a delay caused by the curvature along the route. These are quiet effects, but they are real and add up in precise work. Time is not an illusion. It is flexible. Like light and like space, it bends under rules we can write and test. GPS whispers those rules every second. Clocks on planes and satellites echo them. Light from galaxies near clusters shows them by arriving in curves and delays we can model. Gravity is not only a pull on our bodies, it also shapes our minutes and hours. At small scales, the story shifts again. The quantum world does not give us clean tracks and fixed positions. It gives us probabilities. Objects blur into clouds of chance, and what we can predict are the odds for different outcomes. The tidy lines we draw in our heads fail because the level of detail we want is not available from nature, no matter how careful we are. The electron is the standard example. Early pictures of the atom showed electrons orbiting a nucleus like planets around the sunday. That image is simple, but wrong. Electrons do not circle in tiny loops. They occupy regions where they are likely to be found, and those regions have shapes set by energy and by the pull of the nucleus. When you try to pin down position very precisely, momentum becomes less certain, and the other way around. This is Heisenberg's uncertainty principle. It is not a flaw in our tools. It is a rule of the small world. You can think of an electron's presence as a probability cloud. The cloud is dense where the electron is likely and thin where it is unlikely. There is no single track to draw from A to B. When you observe the electron with a strong enough measurement, you get a position, but the act of measuring changes the system. Before the measurement, the best you can do is describe the cloud and how it evolves. The double-slit experiment makes this clear. Send electrons, one at a time, toward a barrier with two narrow openings. If they were tiny bullets, you would expect two bright bands on a screen behind the barrier. Instead, you see an interference pattern, many bright and dark bands. It is the kind of pattern waves make when they overlap. Each electron arrives as a single dot, but over time, the dots build a wave-like picture. If you place a detector to learn which slit each electron passes, the interference pattern goes away, and the two-band picture returns. What you choose to measure matters. You can measure which path, or you can see the wave pattern, but not both at once. This wave-particle duality is not limited to electrons. Photons, particles of light, neutrons, and even atoms and simple molecules show related behavior in careful experiments. As objects grow larger and interact more with their environment, the clean quantum patterns are harder to maintain, but the principle is the same. Straight lines in the quantum world give way to distributions and waves. The laws still have order. They are just written in a different language. Inside atoms, electrons occupy orbitals. Orbitals are three-dimensional patterns: spheres, dumbbells, rings, and more, describing where an electron is likely to be found. They are not tracks. Chemistry depends on these shapes. The way atoms bond into molecules follows from how their orbitals overlap and share electrons. The solid world metals that conduct, insulators that resist, semiconductors that switch emerges from how electrons fill and move among these allowed states. The math that guides these clouds is Schrödinger's equation. It tells you how the wave function, the object that encodes the probabilities, changes with time. Solve the equation with the right boundary conditions, and you get the allowed energy levels and the shapes of orbitals. You do not get a single path. You get a rule for how likelihood spreads and shifts. Even though the outcomes are probabilistic, the rules for those probabilities are precise. Quantum tunneling adds a new twist. In classical physics, a particle that lacks the energy to climb a barrier simply turns around. In quantum physics, the wave function extends into and beyond the barrier. There is a chance the particle appears on the far side without ever having enough classical energy to go over the top. This is tunneling. It happens in radioactive decay, in electron flow through very thin layers, and in the core of the Sunday fusion in the Sun relies on tunneling to let nuclei get close enough to stick together. Without tunneling, the Sun's core would be too cool for fusion by ordinary rules. Quantum behavior also shows up in entanglement. Two particles that interact can become linked so that their measurements are correlated beyond what classical physics allows. Measure one here, and you can predict the result for the other there, even when they are far apart. No usable signal travels faster than light. The correlation cannot send a message, but the statistics defy any picture of separate, hidden properties set in advance. Experiments violate Bell inequalities, which are tests designed to separate classical hidden variable theories from quantum predictions. The result supports quantum mechanics. The world at small scales does not follow simple local rules for all properties at once. All of this sounds remote, yet modern devices depend on it. Lasers rely on quantum rules for how atoms emit light. MRI scanners use nuclear spins and their quantum behavior in magnetic fields. Computer chips are built from materials whose electrons obey band structures given by quantum states. Tunneling underlies flash memory and scanning tunneling microscopes. Even the global systems that need relativity also need quantum physics to build their clocks and receivers. The two theories work in different domains, but both are essential. If the quantum world is so uncertain, why does everyday life feel stable? Because when huge numbers of particles act together and interact with their surroundings, quantum possibilities narrow into classical outcomes. This process, often called decoherence, suppresses interference effects. Apples do not tunnel through tables because the probability becomes unimaginably small. Chairs do not blur because their states are constantly measured by air, light, and internal vibrations. The straight lines and steady paths of daily experience are averages over enormous underlying detail. At the smallest scales, then, the straight line fades as a useful idea. Paths become spreads. Outcomes become chances with rules. Yet the rules are firm enough to build technology and explain stars. Time bends with gravity and motion. Light bends with media and mass. Particles bend in a different sense by trading single tracks for probability waves. In each case, the simple line is a local tool, not a universal template. Relativity and quantum mechanics can feel far apart, but they share a theme. The world is set by relationships. Motion relative to mass changes time. Measurement relative to a system changes what can be known. Geometry and probability take the place of rigid, absolute scripts. When we respect those relationships, our models predict what we see, from GPS fixes to black hole signals, from chemical bonds to fusion in the Sunday. The picture that remains is steady. Time rates depend on where you are and how you move. Light follows the best path allowed by its surroundings. Matter at small scales follows rules that deliver probabilities, not single lines. The large world emerges from the small when many parts interact. With the right corrections and the right level of detail, the curves and clouds add up to the reliable scenes we live in every day. Even the smallest excitations of matter do not trace neat lines. At tiny scales, they spread, interfere, and choose outcomes by probability. At larger scales, organisms that last tend to build and move with curves. That pattern did not appear for decoration. It survived because it works. Over many generations, small advantages accumulate. Shapes that move loads smoothly, route flows gently, and scale without constant redesign outcompete shapes that crack, stall, or waste energy. The result is a recurring toolkit: spirals, arches, coils, and branching trees. A snail shell is a clear example. It grows as a logarithmic spiral, which means the shell expands while keeping the same overall proportions. The animal adds material at the open edge. It does not rebuild the whole shell each time it gets larger. The curve spreads stress around the spiral, resists crushing, and gives the snail a safe chamber without heavy walls. Similar growth rules show up in ram horns and narwhal tusks, where the spiral helps keep weight near the head and spreads impact forces. A seahorse's tail wraps a branch and holds tight with little effort. Sunflower heads arrange seeds in interlaced spirals that pack space efficiently. These patterns are not copied from a single template. They arise because they solve physical problems with minimal cost. Curved claws hold better than straight spikes. A hawk's talon is a hooked lever that concentrates force at the tip and resists twisting. A cat's claw retracts along a smooth arc to stay sharp. Prehensile tails curl to grip and stabilize, acting like springs that store and release energy as the animal moves. Our own bodies rely on curves. Foot arches spread load and return energy with each step. The spine's gentle shape balances the head over the hips, while allowing the torso to bend and twist. Ribs form a flexible cage that expands with breath. At the molecular level, DNA is a double helix because that geometry makes the molecule compact, stable, and accessible for copying. The shape is not a visual flourish. It is chemistry finding a low-energy, useful form. Curves often beat straight lines on efficiency. A dome or an arch carries force into supports without a sharp stress point. Birdwing bones are curved and tapered to resist bending with less material. Shells withstand pressure with thin walls because the curve spreads the load. In fluids, gentle bends preserve laminar flow, orderly layers that slide with little mixing, while sharp corners create turbulence. Blood moves more safely through vessels that bend and branch. Rivers meander to shed energy gradually, rather than cutting destructive channels. Plants climb by coiling tendrils. The curve grips without heavy structure. A dolphin's fluke sheds water in smooth vortices that increase thrust. A cheetah's spine flexes in an arc to extend stride length and store elastic energy. Each case shows the same trade. Curved motion and structure deliver performance with lower cost. Natural selection does not aim for curves. It holds onto traits that help survival and reproduction. If a spiral saves material while staying strong, or if a bend protects tissue from stress, variants with those features tend to persist. Over time, many small wins add up. You see the outcome as a shape that looks refined, because failures have been removed by time. Inside cells, proteins fold into compact, curved forms driven by chemical forces. A small misfold, a wrong bend, can break function and cause disease. The exact curve of a protein's active site decides which molecules fit and which reactions proceed. Growth patterns favor curves too. Phyllotaxis, the arrangement of leaves, petals, or seeds, often uses the golden angle, about 137.5 degrees, between successive elements. That spacing distributes parts evenly around a stem or disc, minimizing overlap and shadow. No plant computes the angle. Local growth rules and competition for space lead to that arrangement because it packs well. The result is a spiral lattice that fills the area efficiently as the plant grows. Camouflage also reflects curved logic. Stripes and spots break outlines into soft edges that blend with branches and shadows. Hard, straight borders catch the eye. Rounded transitions hide shape. Straight structures do exist. Quills, insect legs, spines, but they usually connect into systems of joints, tapers, and arcs that handle motion and load. Behavior follows the same rule. Animal paths curve to follow contours, avoid obstacles, and ride wind or current. A direct line rarely stays optimal in a changing environment. Humans embraced straight lines early because they are simple to mark and easy to build. Grids make land easy to divide and streets easy to name. Rectangular rooms use repeated components and make furniture simple to place. The Industrial Revolution amplified this tendency. Standard parts and straight edges speed production and assembly. The visual result: walls at right angles, roads in straight segments, mechanical parts with flat faces, feels orderly and scalable. That order has real benefits, but it also hides costs. Sharp corners can concentrate stress. Straight pipes can roar with turbulence. Rigid plans can fail when the ground is uneven or when needs change. As materials, tools, and goals evolved, design began to adopt nature's solutions. Builders returned to arches and shells for long spans and thin roofs. Rounded corners in devices feel better in the hand and resist dents. Car and train bodies learned to shed air with smooth curves. Aircraft wings use airfoil shapes that guide flow and delay stall. Medical stents and grafts match vessel curvature to keep blood flow quiet and reduce clot risk. Ventilation and water systems split and taper like bronchi and arteries to reduce noise and loss. The shift is not about style, it is about performance, safety, and energy. Urban planning has also started to bend. Roundabouts reduce conflict points compared to four-way intersections and keep traffic moving with fewer stops. Parks trace rivers rather than trying to force straight banks, allowing floodplains to absorb water. Paths curve to follow terrain, lowering grading costs and preserving trees. Neighborhoods that mix gentle curves with short blocks can slow cars without harsh devices and make walking routes direct and pleasant. These choices mirror living systems. Spread load, route flow, leave alternate paths, and avoid brittle constraints. Digital design shows the same pattern. Early computers were boxes. Modern products use fillets, rounded edges to reduce cracks and to fit the human grip. Screens render buttons and cards with soft corners because people parse them faster and find them less harsh. Animations with eased curves feel smoother than linear jumps. Underneath, networks use branching paths and redundant links to route around failures. The geometry of the interface and the geometry of the infrastructure both lean away from rigid lines when reliability and comfort matter. The point is not that straight lines are bad. They are powerful tools. They let us mark, measure, and repeat. They give us frames, grids, and references. The better rule is to use them locally, where loads are simple and distances are short, and to let curves take over where flows, forces, or growth need room. Nature has tested that rule at scales from DNA to deltas. We can read the results and borrow what fits. Examples make the case concrete. A thin, straight panel may crack at a right-angled notch. Add a radius, and stress drops. A long, square duct may boom with turbulence. Add bell-mouth inlets and smooth bends, and the sound fades while airflow improves. A rigid grid street plan moves vehicles quickly at low density, then locks up at high density. Add curves, parallel routes, and staggered intersections and resilience improves. A rectangular building exposes large, flat faces to wind. A rounded one sheds gusts more evenly. In each case, curves distribute change rather than resisting it until failure. Evolution's library is full of these answers. Beetle shells use corrugations and domes to be strong without weight. Spiderwebs blend radial lines with spirals to absorb impacts and localize damage. Whale fins use bumpy leading edges, tubercles to delay, stall, and improve control. Engineers have copied each of these features for fans, wings, and blades. In footholds and gloves, textured curves increase friction without sticky chemicals. In shoes, rocker soles use arcs to smooth the roll of the foot and reduce joint load. The same math appears again: guide flow, spread stress, pack area, and allow small shifts. Larger systems benefit too. Power grids that branch and reconnect can island sections during faults and keep service elsewhere. Water networks with loops maintain pressure when a main is closed. Internet routing protocols prefer multiple paths, so data can detour. These designs look messy compared to straight hierarchies, but they fail less dramatically because they are not forced through a few hard corners. Nature arrived at that logic early. Corals regrow from fragments. Fungi reroute around obstacles. Trees heal around wounds and push new branches where light returns. Our minds track these shapes well. We recognize spirals and trees quickly. We find fractal edges familiar because they match coastlines, leaves, and clouds. A curved facade or a winding path often reads as calm because it echoes environments where humans evolved. That response is not an argument for copying every vine, but it is a reminder that usability sits not only in function, but also in perception. Designs that fit our senses and muscles reduce strain and error. The same arguments reach down to the scale of tools and up to the scale of policy. In a clinic, a curved catheter tip follows vessels without scraping. In a school day, schedules with short arcs of effort and brief rests sustain attention better than long, straight blocks. In disaster planning, levees that work with floodplains curve flows into storage rather than forcing water against a wall. In farming, contour plowing follows hills to reduce erosion. The curve, again, reduces peaks and spreads loads over time and space. There is still a place for straight runs. Bridges need straight elements in trusses. Rulers need straight edges to measure. Data tables need columns and rows. But the world that holds these tools is round, rough, and variable. When we design as if it were flat and uniform, we spend energy fighting reality. When we design with the grain of the world, with curves where flows run, with branches where area must be covered, we spend less and get more. Look across biology and build systems, and the pattern is consistent. Curves lower stress and guide motion. Spirals scale growth without redesign. Branches reach further with less material and add backup routes. At small scales, Quantum rules replace lines with probabilities. At large scales, gravity turns straight paths into geodesics. Between those extremes, fluids, tissues, and structures work best when they bend a little. We can keep straight lines in the toolbox and still let the arc set the plan where it fits. What seems like ornament is often the record of function. The coil in a ram's horn stores energy and protects the skull. The swirl in a fern packs leaves as the frond unfolds. The arch in a foot stabilizes and springs. The fillet in a beam prevents a crack. The rounded phone sits better in a hand. The roundabout reduces crashes. The catenary cable hangs in the shape that spreads weight. Each curve is earned by use. If you look for confirmation outside the lab, you see it quickly. Paths people actually walk, cut gentle diagonals across rigid lawns. Planners call them desire lines. Rivers push back against straight channels by eroding one bank and building the other until bends return. Traffic spills from oversimplified arterials onto side streets, unless multiple curved routes share the load. Wherever a rigid plan meets a variable world, curves reappear. They are not rebellion, they are equilibrium. Curves do not guarantee virtue. Bad curves exist: blind on-ramps, awkward handles, confusing interfaces. The point is not to bend for its own sake. It is to let physics and physiology say where to bend, where to branch, and by how much. Nature's record is our guide. Avoid sharp transitions in flow and force. Allow multiple paths for resilience, and use shapes that scale. When those rules set the geometry, systems last longer, need less energy, and fit the bodies and landscapes they serve. There is a reason the curve feels reassuring. It softens where corners concentrate force, and it guides where angles resist. Once you learn to look for it, the pattern shows up almost everywhere. Moon paths and tidal arcs, a sleeping cat's tail, eddies in a mug. The curve is not decoration. It is an efficient answer to common problems. Guide flow, balance forces, distribute energy. Arches hold bridges, not because they are poetic, but because they send load into the ground smoothly. Spirals let growth scale without redesign. Coils, rings, and loops appear because they work under pressure, heat, wind, and time. Architecture learned this long ago. Aqueduct arches, domes, and vaults survive because curved masonry keeps compressive forces where stone is strong. The same logic runs through engineering today. Pressure vessels are rounded to avoid stress rises. Airframes and vehicles are streamlined to move energy around rather than let it pile up. Rounded fillets at beam joints prevent cracks. Every practical curve is solving a specific constraint. Nature does the same work at larger scales. Gravity shapes matter into spheres and disks because those forms minimize energy for a given mass. Planets settle into slightly squashed spheres. Orbits are ellipses, free-fall paths that close on themselves. Spiral density waves cross galactic disks, organizing star formation without rigid arms. Even space-time adds its own bend. Mass curves the geometry, and light and matter follow the straightest possible routes within that curvature, routes that appear curved to us. The behavior is not a flourish, it is the geometry doing its job. Light shows the rule in ordinary settings. In air, water, and glass, it bends to minimize travel time given local speed. And that refraction paints rainbows and halos across the sky. Around massive objects, it bends because space-time is curved. and that lensing stretches distant galaxies into arcs. At small scales, wave behavior replaces thin, straight rays with interference and diffraction. The sharp line collapses into bands, fringes, and soft edges. The same pattern, no hard corners, if a smoother route can lower cost, reappears in optics again and again. The curve also governs how things grow. Logarithmic spirals let shells expand while keeping shape. Horns coil to keep weight near the body and spread impact. Leaf and seed patterns use spiral phyllotaxis to pack area efficiently without obstructing light or flow. These outcomes are not pre-planned drawings. They are the result of local rules. Under constraint, add material where stress is low. Stop where stress rises. Rotate by an angle that reduces overlap. Over many cycles, the curve emerges. In motion, curves are the safest way to change state. Fluids transition from laminar to turbulent. At sharp turns and sudden expansions, gentle bends and tapers suppress waste and noise. Gates rely on arcs. A cheetah's spine flexes and releases like a spring. A dolphin's fluke sweeps in smooth oscillations to shed vortices cleanly. Tendrils coil to store and meter force as plants climb. Even at rest, our bodies depend on curves. Foot arches distribute load and return energy. The spine's shape balances the head without a constant muscular fight. The ribcage expands because its curved struts can rotate slightly at their joints. The preference is not aesthetic. It is a general property of systems that must move matter or information under limits. Branching plus curvature carries resources to many points with little material and built-in redundancy. That is why lungs and trees look like variations of the same plan. It is why rivers develop meanders that slow erosion and spread floodwaters. It is why neuron arbors and fungal networks explore large volumes without committing to one brittle path. Human designs increasingly follow suit. Roundabouts reduce conflict points and smooth traffic. Bridges add arches and cables that find natural catenaries. Medical devices trace vessel curvature to keep blood flow quiet. Buildings add curved corners that resist chipping and ease airflow. Interfaces use eased motion because our eyes track it with less effort. Networks route along many paths because redundancy prevents single-point collapse. In each case, performance improves not by adding power, but by letting geometry do more of the work. Straight lines still matter. They make measurement clear and construction efficient, but they are local tools. Over long distances on a sphere, the true straight path is a great circle that looks curved on a flat map. In space-time near mass, the straightest path a geodesic bends as seen in ordinary coordinates. Inside materials, the shortest route for stress is rarely a sharp corner. The practical rule is simple. Use straightness where conditions are uniform and use curves where conditions change. The same rule scales down to the quantum domain. The old picture of tiny balls on exact tracks fails because position and momentum cannot both be fixed beyond certain limits. Electrons live in orbitals probability shapes set by boundary conditions rather than thin loops. Tunneling carries particles through barriers they cannot classically climb. Entanglement ties outcomes together without a classical path between them. The straight line is replaced by a distribution that evolves by precise equations. The curve here is abstract, a shape in probability space, but the effect is the same. A single rigid path gives way to a family of allowed behaviors, and the system takes the one the rules permit at lowest cost. At the other extreme, relativity finishes the argument. Time rates change with speed and gravity. Signals follow bent routes in curved space-time. Clocks need correction when they leave Earth's surface, and navigation relies on those corrections. None of this is optional. It is how the world works when you measure carefully enough. The fact that daily life feels straight and steady says more about our scale and tolerance for error than about the deeper rules. If you prefer a test in the field, watch what people actually do. On a new lawn, footpaths appear as gentle diagonals across the planned grid desire lines that pick the real minimum effort route. In a river, cut straight by machines, bends reform as flow plucks at one bank and deposits on the other. In cities, rigid arterials clog until a set of alternate, curved feeders shares the load. Systems return to curves when the imposed straightness ignores cost. This does not make straight planning a mistake. It makes it a starting point. A rectangle is fast to lay out. A grid is easy to extend. A straight canal is easy to survey. Then reality adds detail. Wind, water, traffic, growth. The durable solution blends the quick clarity of the line with the staying power of the arc. Good streets keep some grid for legibility and add curves and diagonals to carry real movement. Good structures keep straight beams and add fillets and shells where load turns. Good codes keep linear schedules and add cycles that match how attention and effort actually ebb and flow. You can see the same pattern in habits. Flat effort lines always up, always on break. Curved plans, bursts and rests last. Learning works better with spaced repetition than with one straight cram. Fitness improves with periodization. Attention benefits from focused sprints and short, regular recovery. Even sleep follows staged cycles. Where flow matters, curves matter. None of this is license for vague thinking. The curve is not an excuse to drift. It is a reminder that the shortest reliable route in a real environment rarely looks like a ruler stroke. It bends to avoid loss. It loops to gather strength. It branches to keep options open. It aligns with the structure beneath so that energy goes into motion rather than into friction against constraints. Stand back, and a plain summary emerges. Curves distribute stress, conserve energy, and fit complex spaces. Spirals scale growth without redesign. Branches cover area with little material and add resilience. Great circles shorten travel on a sphere. Geodesics guide motion in curved spacetime. Quantum waves replace rigid tracks with lawful probabilities. In each case, the curve is not a flourish on top of physics. It is the form physics prefers when asked to move, to hold, to connect, and to last. So the next time a route arcs north before turning west, or a bridge rises in a shallow bow, or a tool feels better because its corners are rounded, the reason is the same. The system has found a path that costs less and breaks less. The line still has a place, but it is not the measure of all things. And with that, the pattern is easy to keep in view. Streets and rivers, shells and domes, orbits and rainbows. What looks like elegance is often economy. What reads as grace is usually stability. What feels soft is typically strong. The world lowers its risks by bending, and we move through it more easily when we let that geometry lead.